Hello! Welcome to Forces. We're going to start by doing free body diagrams. A free body diagram is when we take an object and we examine it in terms of a square or just a little point and look at the forces that are interacting with it. The purpose of that is so that we can get all of our forces straight. Because the thing with forces is we're going to end up having a lot for each problem. We're going to end up having like 4 to 10 different forces interacting on an object at any given time. But that's like all the way to the advanced stuff. You don't need to be afraid of that right now. To start with, we'll work with 2. So a free body diagram is going to help you figure out how to keep your forces straight. So we're going to practice drawing these out. And I'm going to draw them both ways, okay? So we'll start with the first one. It's just very simple. It's a box full of jokes that I have misplaced somewhere, which is why I'm not very funny. It has a mass of 300 kilograms. Draw a free body diagram representing it. So the first way is we just draw a box. It doesn't matter if it's a box, it doesn't matter if it's a car, it doesn't matter if it's a frickin' airplane. We make it a box. So, first force acting on it is the force of gravity. Everything on the planet Earth has a force of gravity acting upon it. Okay? So, now because this thing is resting on the ground, it has a force being pushed on from the ground. The ground is pushing back on this thing. If it didn't have a force on the ground, it would actually be falling. So if we didn't have any ground below it, it would be falling. And then we wouldn't have a reactionary force. But in this case, the box is sitting still, so it has a reactionary force. Force normal. Now, there's no gravity going side to side. There's no natural force that moves side to side. So if a box is sitting still, and you're drawing a free body diagram of it, you don't have any side to side forces. There's nothing there. It's just the down and the up. So this is a representation of Newton's third law. Force of gravity going down, the floor pushes back with a reactionary force of what we call force normal. It's important to recognize force normal because it's what we're going to use when we deal with frictions. We're not there yet, but we will be. So the other way to draw this is just by doing a little dot. And I like these better, I feel like they're more professional, but you can do it however you want, either a box or a dot. It's got to be either or though, okay? We need nice, simple shapes. So the way you do this is dot, arrow down, force of gravity, arrow up, force normal. Nice and simple. Number 2, draw a free body diagram of a guy pushing a box. So, let's draw that one out. Box. Again, it's on the ground. So there's a force of gravity and there's a force normal. Force of gravity. And force normal. Now, obviously, this guy's pushing the box. So he's applying a force to the box. The way we draw those is the correct way, and you won't always see me do this because I don't always do it the correct way. I don't expect you to either. But I want you to know that the correct way to draw force is always as a pull. It is always from the box out. So the guy pushing on the box is the force of that guy. Okay? It's always going outwards. We wouldn't draw it here because that's not the correct way. Although you will see me do that because I'm not very good at this. Okay? So we can also put in, we're assuming he's pushing this along the ground. There is a force resisting him. Okay? He might be accelerating, he might not be. He might be moving at a constant speed. We don't know. All we know is he's pushing the box. But because he's on the earth, because there is a force of gravity, there's also a resulting force of friction. So we're going to add that in as well. Okay? And then the professional way to do this, the dot, down, force of gravity, up, force normal, to the side, force of that guy, and to the other side, force of friction. Muy bien. Okay, so that's number 2. See, this is it's really quite simple. We're just drawing a box or a dot and putting some arrows on it. Right? Okay. So let's go ahead to number 3. Draw a free body diagram of this guy pulling a box. He's pulling it this time. Okay? So it's actually going to end up being the same thing. It doesn't make a difference to us whether someone's pulling or pushing a box, because when we're drawing a free body diagram, we neglect all of those shapes. Now, normally, that shape, we have a box, we have a guy pulling on it, hey, there's a guy. Boop, boop, boop. He's got a smiley face, and he'd be pulling on this rope, he'd be causing a tension in this rope. It would be a force of tension. That's also in newtons. We're not really going to get into those, but you should know about it. But this is the drawing itself. This isn't the free body diagram. The free body diagram is this. And it's got a force of gravity. It's got a force normal. And then it's got a force of tension of the rope. That's a force of tension. If we were looking at the guy, he'd be applying a force to the rope. But we're looking at the box. The box has a force of tension, and that's all of its external forces pulling it. Now, obviously, again, it's on the ground. It's got a gravity. So, it's got a force of friction, resisting that force that's trying to pull it along on the x direction, okay? So now the more professional way, draw a little dot. Beep, 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 beep. Force of gravity, force normal, force of tension, force of friction. Okay, great. So those are our first three. Nice and simple. Do you see them? Are they clear? Can you see them on the camera? Beautiful, beautiful drawings, right? I'm quite the artist. Okay, I'm gonna erase what I've drawn, and then we'll start with number 4. Okay, number 4 has a car in motion, right? Motion. So the thing to remember is an object at rest stays at rest, or an object in motion tends to stay in motion unless acted upon by an outside force. And what is an outside force? How do we define a force? Well, we define a force in terms of mass times acceleration. MA, right? So if we have a force, a net force on an object, we actually have a resulting acceleration. So just because something has a constant velocity doesn't mean that it has a net force of anything other than 0. If something has a constant velocity, it actually has a constant net force of 0. 0, okay? So let's go ahead and draw the car that has a constant velocity. Again, starting with the box. Remember, either one of these are acceptable. Obviously, it's driving along on the ground. It's not floating in the air. It's got a gravity acting on it. And then every time we've got a gravity acting on something, a force of gravity, and it's on the ground, it's not just falling through the air, it has a reactionary force of the force normal. Now, this force normal is any time something is pressing against something that's not giving way. So if I were Batman hanging on a rope, scaling up the side of a building, I'd have a force normal of the building pushing back against my feet because I'm not crashing through the building, right? Okay, well, I would because I'm heavy. But Batman, he's lean and in shape and he wouldn't. So we have motion. Well, there's something supplying the motion to the car, right? It's the engine. We have the force of the engine. So force, engine. But we're moving at a constant velocity, so there's some amount of force pushing back on the car, keeping it from going faster, from accelerating. So we have an equal and opposite force, and that results in a net force of 0, which results in an acceleration of 0, which results in a constant velocity. I want you guys to see this, so we'll call this force of friction plus force of drag. Because, I mean, we really have both. We have friction inside the engine, and we have drag outside the car that's pushing against the car, all that kind of stuff. But I really wanted you guys to see this, just as an example of something in motion that still has a constant net force of 0, that still has 0 acceleration. So it's moving, but the total forces are just totaling at 0. It's still in motion. Remember, everything in the universe is in a constant state of motion. We really don't have a reference point of stillness. We don't have a 0. Remember the professional way? Using a dot. Force of the engine. And then the force of friction plus the force of drag. Great. Nice and simple. So what about if the car was accelerating? Well, our forced body diagram would actually, or our free body diagram, would really look the same. I mean, it being in motion just means the force of the engine is exceeding the force of friction and the force of drag. So we're basically going to draw the same thing. Force of gravity, force normal, and then we'll draw a longer arrow, force of engine, and then a nice little short arrow, so be a little over dramatic with it, just to really signify that. Force of friction plus force of drag. And I don't expect you guys to know exactly what the force acting against it is. You could just say it's got a force. It's force 1 and force 2. You could say things like that. I'm basically making these up as I go. We'll get into force of drag and force of friction eventually, but it's not important right now, okay? So then the professional version, dot, force of gravity, force normal, force of engine, force of friction and drag. Okay? Bingo, bango. Okay, so moving on, we're going to draw a free body diagram of Batman punching the Green Lantern. Hint! There are 2 bodies here. So we're going to actually draw 2 separate force diagrams, one for each object. This is the standard procedure for when you have multiple objects. If you have multiple objects in a system, or if you have multiple objects interacting with each other, you're going to draw multiple free body diagrams. Okay? So first we'll do Batman, because Batman is way cooler. He has a force of gravity acting on him. He's got a force normal acting the other way. And he has a force of his punch going outwards. Force of punch. Okay? Now, remember, we have reactionary forces. So if he's punching Green Lantern, his fist is pushing on the Green Lantern's face. Well, his fist just doesn't go through the Green Lantern's face, it collides with Green Lantern's face. So Green Lantern's face is also applying a force on Batman's fist. This is why, if you've ever been in a fight, or you've watched movies where someone's been in a fight, they punch someone, and if it's realistic, they go, ah! Because it hurts their hand. Punching someone in the face causes an equal and opposite force on your hand. So if you break someone's jaw, you probably broke your hand too. So, force of the punch, and then the reactionary force of Green Lantern's face. GF. Woo! And then the professional way. Force of gravity, force normal, and then force of the punch, force of Green Lantern's face. Okay? Alright, now Green Lantern, right? So we'll draw them right next to each other so we can see that dynamic, because we're moving in the X-plane. So he's also got a force of gravity. He's not sinking or flying, at least not right now. Woo! Force of normal, and then he's being pushed backwards by that force of punch, right? Right? But then his face is applying an opposite force. Green Lantern's face. Okay. And then the professional way. Down. F. Gravity. Oh, I should do lowercase g. Sorry, that doesn't make sense. Lowercase g. And then force normal. And then force of the punch. Then force of Green Lantern's face. Perfect. Okay, there we go. That's nice. It's nice to be able to recognize and identify. Okay, next one, an Atwood machine. We're going to be dealing with these a little bit in our Forces lab. An Atwood machine is a nice little doodad that's a mass suspended on a string that goes around a pulley and string, rope, whatever you want. And then on the other side, it's got a different mass. It could be the same mass, it could be a different mass, but I mean, if you really think about that, if I've got 2 masses, well, force is an acceleration. If they're the same mass, then when they're at rest, they're going to remain at rest. And then when they're in motion, they're going to remain at a constant velocity. So what's really neat about an Atwood machine is if I built a giant one, I could have these two huge masses. Maybe I've got one that's supposed to be a counterweight and another that's lifting this giant cement roof of the Vatican up into place so that I can, fix it into place because I'm constructing something in the 1700s. Really, I mean, if I had these equal masses, all I would have to do is then lift up a little bit on the one mass that's on the ground, and it would have a constant motion going all the way up. And then someone could stop it just by pressing on it. It's actually really cool. It's a really cool concept, and I wish we could play with several thousand tons of masses, but we can't. So we got mass 1, mass 2, and then we'll do a free body diagram for both of these. Okay? So each one has really the same two forces: force of gravity and force normal. And then the other one has force of gravity and force normal. And then the professional version. And I say professional, but I mean, I'm like the farthest thing from professional. I really hope you guys have noticed that by now. Force normal, okay. Force of gravity and force normal. Great. Okay, so the way this would work is if this mass was larger, well then the force of gravity on it would be greater. There would be a greater force over here, resulting in a motion this way. If we had the opposite, if this had a bigger mass, let's say this one's 1,500, and this one's only 1,200, well then this would have a greater force of gravity, resulting in motion in this direction, okay? But there's still only a motion in the y. It's a force of gravity versus a force normal, and I should really draw an arrow there. And we could call that force normal the force of tension in the rope as well, okay? Okay, great. So moving on, we have one last free body diagram to draw. It is a modified Atwood machine. So the thing to know about pulleys, and if you've taken any classes that deal with simple machines, you should already be aware of this. But a pulley, it really doesn't do much to the forces or motion involved. All it does is change the direction. So if I'm looking at a problem with a pulley, it's really just changing the direction of the forces, okay? It's not adding to the forces, it's not subtracting from the forces. I mean, there's a little bit there, just because it itself is rotating, but whatever. So a modified Atwood machine is looking at something like this. So we've got a mass here, and it's connected by a rope to a pulley, which is connected to a table, or a much larger object, I don't know, a plateau or something, which is then connected to a mass hanging off the side. This mass gets affected by gravity pulling it down, which then acts as a net force on this mass, pulling the whole system to the right and downwards. It's actually really cool to play with. And this is actually what we're going to be playing with in our forces lab. You guys are gonna have fun with this. Hopefully fun. I mean, my money's on fun, but your money might be elsewhere. So, drawing free body diagrams of both of these, remember, we've got two blocks. So we'll go ahead and draw two boxes right away. We've got M1, M2, and M1 has a force being pulled this way. We'll call that F1, that's our first applied force. And we've got a force resisting that, and we'll call that the force of friction. And my money's on F1 being bigger than F friction, and that we'll have motion in this direction, we'll have an acceleration. But we wouldn't necessarily, if this were a rubber block and this were a small mass, it wouldn't move. But still, M1 has those two reactionary forces, F of gravity and force normal. And that force of friction is going to be based on that force normal. You don't have to know that yet, but we'll get to it. So then our mass 2, it only has one dimension of forces, force of gravity and force normal, which force normal in this case is also a tension force. Okay? We're not really going to get into tension very much in our unit, but it's good to know. If you get into AP physics, you're going to use tensions a lot, like a lot. Okay? So, the professional version, a little dot, a force of gravity, a force normal, a force 1, we're calling it force 1, and a force of friction. And then for this one, Very simple. Down, force of gravity, and up is force normal or force of tension. Either one would be acceptable. Okay? So you can label these forces pretty much however you want. If it works better for you to call them all by numbers, like F1, F2, F3, F4, that's how I did it when I first learned it. Now as I try to explain it in different ways, I try to use letters and numbers and call it applied or friction kind of interchangeably, just so I have a plethora of different ways to name it, just so that you guys can understand it in different ways. But you can name these however works for you. The important thing is that you recognize that the source of this downward force on almost all of these is the force of gravity. And that if something is resting on a tabletop, if it's sitting there, being held up, well, then it's got a reactionary force of force normal. Even if it's lightly held up a little bit, if it's still resting on the ground is still pushing against it. Any amount of forces interacting, any objects pushing on each other, they're going to be pushing from one to the other and the opposite to the other one. This one's pushing this way, this one's pushing this way, so they both have a force going this way and this way. Okay? Great. Thanks, guys. See you later.